This lesson deals with the 555 timer SPICE model and the 555 timer datasheet. You can find these notes in the ECE402 ebook in Chapter 7 starting on page 14. PSpice has a macro model for the 555 timer, but it's for the CMOS version of the timer, and it's called 555D. We're actually using the bipolar one, and there's some differences, but this model has a lot of inaccuracies in it. In fact, it can hardly predict anything correctly. I have fixed that model up, but I decided not to include it in the course anymore because it's not really what you would get if you were just using the library by itself. So what else can we do? We can try to make up our own macro model, and in fact I tried to do this many years ago, but it's pretty complicated and we didn't finish the whole thing. So I went back and did what I did in other cases, and that is to go back to the transistor level schematic of the 555 timer. Let me show you this picture of what that schematic looks like. This was actually in another textbook, and I scanned it and then labeled all the node numbers in here so you could do a SPICE simulation, and also highlighted where the different parts are in here. So here in this grouping of transistors is actually the threshold comparator. This group down here is the trigger comparator. This is the RS flip-flop, and this is the inverter part of the chip. Here's the discharge transistor, and here's the reset transistor. Notice here that the diode that's created here is actually a shorted base collector of a transistor to make a PN junction from a transistor. It's a trick we use in IC design. You can see how I numbered all the nodes here, and I'm going to use this for the simulation. Now in this model I had to iterate the BJT parameters, and I used parameters that came out in some publications around the 1970s. So things have changed over time, but this set of numbers was pretty good at roughly getting the functionality of the chip. So let me create a symbol for the 555 timer. Now for an op amp we have a triangle. For a lot of ICs they just show a picture of a rectangle. Now the rectangle here is shown with basically inputs on the left hand side, outputs on the right hand side, power type issues on top, and ground on the bottom. And so you can see here the node numbers, are actually the node numbers of the chip are not like you would see on a picture of the IC itself. So this is really my equivalent symbol for the 555 timer. This is sort of what I've been using in the class notes also. Let's take a look at the SPICE file. I've included this file in the library file that's on my homepage for ECE402. And you can see here there's quite a few parts in here. Got 16 resistors. Actually 26 transistors, have 2 here that are labeled A and B. It's a trick of doing multiple collectors. And then here are the models that I used for the transistors, and I had to iterate these to try to get them to match some of my lab data. And they were iterated off of a magazine article that was published in the 1970s of actually a 741 op amp chip that was measured and got some of the transistor parameters. Now this won't run on the student version of PSpice, but it will run on the full version of PSpice. You can get to the full version of PSpice through the DEX remote logins. I believe this will also run on LT Spice. No matter what the model is you're going to use for any IC, one way to test it is to come up with a set of test circuits, and that's to build circuits that we are familiar with and kind of know what the answers are supposed to be. So whether we're using a full transistor schematic to simulate this chip, or we have a model, like I did with the 555D model in the PSpice library, I can see whether the model works or not. So the model stable is probably one of our first circuits that we talked about, so let's use that to do a test. So I set up a 12 volt power supply, and I need a pulse that's going to go from VCC to 0, so that's what this is, from 12 volts to 0. I did a time delay of 50 microseconds, and then a rise time and fall time that's equal to my print step, and then a pulse width of 5 microseconds. Let's take a look at this on the bottom. So I'm going to go from 12 volts to 0 volts for basically 5 microseconds and come back up again. This looks like it's just going straight up and down, but the minimum value you can put here is actually the print step. So I'm doing 2,000 data points. So this appears to be instantaneously dropping and coming back up again, but in reality it has a slope to it. Okay, I plotted here node voltages 4 and 2. Let's just see where those are. So node voltage 4 is my input, that's my pulse. And V2 is the voltage across the capacitor. And you can see it starts out here and starts to charge up. and gets to 8.02 volts and then comes back down again. 8 volts is 2/3 of 12 volts. So that looks like it's pretty much on track. And then the pulse width here, we can see comes up, actually overshoots and rings a little bit, and then comes back down again and goes to 10.616. And again, I'm using a 12 volt power supply. We'll compare this to the data sheet and we'll see how close we are. But at least for our initial calculation here, let's calculate the natural log of 3 times R1C1, and that turned out to be 99.97 microseconds, and we're reading 100.944 microseconds. The reason why they're not exactly the same is that this is a very accurate model, and this represents the error between the ideal and the real. But you can see here that this is modeled correctly because I'm getting the right results. Now, on this copy, it's a little bit hard to see, but there's a little bit of overshoot and ringing here. When I first did the simulation, I felt that this was an error in the modeling, and I tried to get rid of it, and I just could not. It has to do really with the capacitance on the substrate and the transistor capacitances. But when I got a fast enough oscilloscope, I noticed that that was exactly what was happening. The scope I was using originally didn't have enough bandwidth, and you couldn't pick that up. So again, the modeling in this case was better than my measurement at the time, but eventually as I got a faster oscilloscope like the Infinium, I was able to see the little spike there and the little overshoot and ringing. Let's use the A-stable as our next test circuit. Now for this one, we don't have a source other than the power supply, but this is an oscillator, so you want to delay the start of it to get basically a ramp rich in harmonics to get the oscillation to actually happen. So here I'm going to take my power supply. I'm going to go from 0 to 15 volts this time. I'll delay it by 0.1 microsecond, and that's actually my print step again, so that's the smallest I can create a time delay. So it'll appear to be almost instantaneous, but there is a slope there. Resistors now are R1 is 3K, R2 is 3.9K, and this is a 0.01 microfarad capacitor. Take a look at the simulation. I'm going to plot here the capacitor voltage, which is node voltage 2, and the output. There's a little bit of delay to start this. We'll talk some more about this with the actual data sheet. Here we're charging up to 2/3 VCC, which would be about 10 volts, and then we discharge down to 5 volts, but you can see here it's 4.8. Some of the non-ideal comparators kicking in, charge back up again, down, and so on. Can you see a little spike and overshoot here? And then we get a one-time shot here, and then we've got the time low, and then the time high, time low, and time high. See what those turn out to be because we have some formulas for that. The natural log of 3 times the sum of the two resistors times the capacitor is 75.8 microseconds. My actual measurement here in the SPICE simulation is 76.911 microseconds. And this again is due to the non-ideal timer that we were using, the full chip simulation. The time that we're low is the natural log of 2 times RC, and that's 20.79 microseconds, and here it's 21.7. And lastly, this interval is the natural log of 2 times the sum of the resistors times the capacitor, and that's 47.82 microseconds. Actual measurement simulation 50.6. All these are a little bit longer than what we calculate, and that's because there's time delays, rise times, fall times, delay times inside the chip. We'll look at this a little bit later in the lecture. This does predict the basic A-stable operation, and this would be a valid model. But remind yourself that this is a lot of transistors, and it will take a long time to do a simulation. Let's next take a look at the 555 timer data sheet. Start with the threshold specifications. Now inside the chip there are resistors, and they're fairly tightly matched, but they're not perfectly matched. That's going to change our reference voltage that we've been talking about calculating from. And there's also input offsets associated with the comparators that we have. So there's two specs in the data sheet. One is for the threshold voltage, and one is for the control voltage. For the threshold voltage, if we're using a 15 volt power supply, typically that would be 2/3 of that, or 10 volts. But it could be as low as 9.4, as high as 10.6. Now the other side of the threshold is the control voltage. And you can see here for the same power supply, you would expect, again, 10 volts for 2/3 of that, but there is a range from 9.6 to 10.4. So again, this is because of the offsets that we have, mismatches in resistors. Now if you use a 5 volt power supply, it's again going to be 2/3 of the value, and again with a tolerance on it. Once you have a chip, and say you're, I don't know, say a 10.3 or something, it doesn't change, it pretty much stays there. So you can compensate for this by changing the values of your R and C. Another spec associated with the threshold comparators is the threshold current. It's because we've got currents that are going to be going into the terminals of the transistors. Now for the threshold comparator has NPN transistors, we'll have current going into the chip. Now what's happening as we're switching is that we're going to go from cutoff to either being active or saturated. So we're going to see a jump in current. Also on page 124 of the data sheet, the typical value is listed as 0.1 microamp for the current that's needed to go into the comparator to get it to switch states. Again, it's going to be going from a case of being, say, cut off to either active or saturated. But this could be as high as 0.25 microamps. Before I go on, let's take a look at the data sheet and take a look at those parameters. Here's our data sheet for the 555 timer. And at the bottom of the page, these are the numbers I'm referring to. So this is page 123. It was part of a book that Signetics put out. Here's that schematic that we showed before. And here's a functional block diagram of the 555 timer. But on the next page is a set of tables with some of the numbers I was picking up, just like other data sheets. So here you can see specifications for the threshold voltage and the control voltage. Those are the values we were just looking at. And then also for the threshold current, here's the typical and maximum values. Looking at the ECE402msu, this is the one that's military grade. It goes from -55 to 125 C. The ECE402msu is from 0 to 70 degrees C. Basically the same circuit, but there are some specs that are slightly different. Now, what is the effect of having this threshold current for the comparator? Prior to switching, the current going in the comparator is basically 0. And so we have this RC charging circuit for our monostable and similar one for the A-stable. And then at some point, as we hit 2/3 VCC, I need to supply a maximum value of 250 nanoamps. Now, the typical is smaller than this, but this would be the most you'd ever have to supply. What does that imply? Well, when you get to that point, the voltage here is 1/3 VCC, because this is 2/3. And the current that's in here, I got to be able to supply 250 nanoamps back in through here. In other words, nothing can go here, but just simply go into here. So if I know the current and I know the voltage, I can calculate the value of this resistance. So if we take 5 volts, which is 1/3 of 15 volts, and divide it by the 250 nanoamps that would say be flowing in here, all diverted to get that comparator to switch, that would be a 20 megohm resistor. So the biggest resistor you could put here is 20 megohms before the thing would stop working because of this specification. Now in the data sheet on page 124, they recommend nothing bigger than 10 megohms, just having a little bit of a safety factor in here. The same thing would be true for the sum of these two resistors. Again, in our data sheet on page 124, there are specifications for the trigger voltage. So typically 1/3 of VCC, so for 15 volts that would be 5 volts. But again, because there are non-idealnesses in my chip, this could range between 4.8 volts and 5.2 volts. On page 125, there's a lot of graphs, one of which is called the minimum pulse width required for triggering. Let's take a look at that. That will be on the following page. So here's 124, here's 125. It's right in the top left-hand corner. Let me make that a little bit bigger so you can see it. So here's the minimum pulse width in nanoseconds, and then here is the lowest voltage level of the trigger. You can see here that this is at basically 1/3 of VCC. So at 25 degrees C, if your pulse just went a little bit below 1/3 VCC, maybe 55, 60 nanoseconds, then what that means is that the pulse would have to be at least that wide. If it wasn't that wide, there wouldn't be enough time for things to propagate through the chip. This is sort of like the idea of input overdrive, because as we go lower and lower on that pulse, we're putting more voltage across those transistors and it'll switch faster. I don't need a pulse width as big as 55 or 60 nanoseconds, but something, maybe around 20 nanoseconds or so. It's very dependent on temperature, so that's very important to keep in mind that if you are doing something that's going to go outside or go in outer space, you have to worry about the swing in temperature. Silicon can work from -55 to 125 C. The other one is on the bottom of this page. It refers to triggers. And this one is called propagation delay versus voltage level of the trigger pulse. So we have to have a minimum width on the pulse, again, which is mostly in nanoseconds. And then once you do that, how long does it take for the pulse to travel through the chip? So again, here's our 1/3 VCC. So at 25 degrees C, we're looking at a time delay of, if you just drop down to 1/3 VCC, just a little bit below that, of 250 nanoseconds. Short, but still there's something there. And this is having to do with, again, response time versus input overdrive. You can see it's changing as you overdrive it, but also there's a delay through the flip-flop in the circuit and the other transistors. But if you overdrive that, you can switch that signal through there much faster. Here you can see for 25 degrees C, it's about 100 nanoseconds. But you have to wait for the pulse to show up on the other side. Just like the threshold comparator, we're going to have current associated with the trigger comparator. This is going to happen when we drop below 1/3 VCC. The transistors are going to go from being cut off to either going active or saturated. So we have to be able to supply a base current. But this time, because we're dealing with PNP transistors, the current is going to come out of the trigger pin. Our table on page 124 of the datasheet says that's typically 0.5 microamps, but could be as big as 0.9 microamps. Let's next take a look at the reset specifications. So we've got a reset transistor, and it gives some specs about the voltage and the current. Now they're showing that schematic of the reset transistor is 2 diode drops above ground, actually base emitter drops. And so the reset pin, for it to do anything, we have to bring the voltage down so we can forward bias that emitter base junction of that PNP transistor. The datasheet on page 124, it says that we need to bring that base pin down to at least 1 diode drop above ground. So then what we got left across the emitter base diode is basically 0.7 volts. But this could again be in a range from 1 volt down to 0.4 volts. So once you drop below these values, then the reset transistor will trigger. We'll take a look at this in an application. There's also a current associated with that transistor, but again, because it's a PNP transistor, it's going to be coming out of its base terminal. And that's going to be typically 0.1, but could be as big as 0.4. Let's go find those specs in the data sheet. Let's go back to page 124, which is page 2 of the PDF. And let's find the trigger specifications. For a 15-volt power supply, here's the voltage at 5 volts. And here's the trigger current at 0.5 microamps. And again, typical, but a maximum value of 0.9 microamps. There's also reset information here. So here's the reset voltage, typically 0.7 and then minimally 0.4 and as big as 1 volt. And under those conditions, what kind of current are we talking about? The 0.1 milliamps and the 0.4 milliamps. And if you were to pull that reset voltage down to 0, that number would go up to 0.4 milliamps and 1 milliamp. Now specifications about the discharge transistor. In the 555 timer datasheet from Signetics, there is no information about the saturation voltage of the transistor. So I went and looked for another datasheet. This is the National Semiconductor LM555, which is now part of Texas Instruments. And they did give a value for the saturation voltage. Again, that's the voltage between the collector and emitter when we saturate. This was actually on page 2 of that datasheet. And typically it was listed as 150 millivolts. If you recall from 302, we were using 0.2 for our typical value, or 200 millivolts. This is going to change depending on how much current flows in the transistor. This is the current in the transistor shown in this data sheet. So the more current we pump into it, the bigger the drop across the transistor. Because again, it's not just a straight line up and down, but it has a slope to it. There's also a current associated with a cutoff transistor because we have a base collector and base emitter diodes that are reverse biased, and of course there's a saturation current. And again, I had to turn to the 555 datasheet from National Semiconductor, and it gave a typical value of 1 nanoamp, but could be as big as 100 nanoamps. Let's next take a look at the output specifications. So our output can be low or can be high. Refer back to the schematic that I showed you earlier. Let's just go back to that. This output transistor here is Q24, and this is either saturated or cut off. Let's take a look at, or actually going active. Let's take a look at some of the specs on that. This is transistor Q24. Take a look at when it's saturated. Again, on our table on page 124, we'll see a list of data of typical and maximums. Here with a 15-volt power supply, if we have the transistor saturated and again, the output would be low, we're pumping current into it, that you could expect about 100 millivolts typically for that transistor saturation voltage. If you pump it up to 50 milliamps, it's going to go up. And again, the maximum will be a little bit higher. But then if you start pumping more current into it, the transistor will go active. When we're sitting over here, we're on this line that goes like this, and then eventually it'll turn the corner and go active. And that's the case here where I've got 2 volts or 2.5 volts across the transistor when I've got over 100 milliamps. The thing I should point out with the 555 timer, there is no current limiting protection on it. So our 741 op amp shuts itself off when we exceed about 25 milliamps plus or minus. The 555 timer will just simply melt if you pump current into it. Fortunately, the first time I played with it, I thought there was a current limiter, and I watched my board and my chip just melt. You'll learn by sometimes smelling your circuit. Of course, if you change the power supply, those numbers will actually change too. Now in the data sheet, there's also a set of plots that shows what happens when the output's low versus the current sink. And this is on page 125. Let's take a look at that real quickly. Let's go to the next page here. So there's 3 graphs here. When the output voltage is low, it's these 3, for 5 volts, 10 volts, and 15 volt power supplies. And you can see the results are temperature dependent. And again, this is a plot really of the collector current versus the collector emitter voltage sideways. This kind of goes back to vacuum tubes and how they show data sheets, but anyhow, this is the collector emitter voltage versus the collector current. And again, it looks like it's a straight line on a log scale here. So we're doing log this way and a straight scale this way. Here's where the transistor starts to go active over here. Now the other case is when the output goes high, and that's our bottom transistor is cut off, and the top transistor, take a look at this on our schematic again, is over here. This is Q23. This may saturate or go active, but let's take a look at our specs. So this node voltage here, I've got 1 diode drop, I've got 2 diode drops, and I got a drop across the resistor. So we're going to see in a little bit is that the voltage here is basically the power supply minus 2 diode drops plus a little bit more due to this. So this won't exactly saturate, it'll stay actually active. And one of the advantages of that is it can switch faster. When you saturate a transistor, it takes a little time to pull it out of saturation. Some of the specs on this. So in our data sheet, again on page 124, our table, that for a 15 volt power supply, if we're sourcing current, again that's the bottom transistor would be cut off, the top one actually is going to go active, we would see a typical output voltage of 12.5 volts with a 15 volt power supply. So again, we got quite a bit of difference between these two. It's about 2.5 volts, and that's because of the drops across the base emitter junctions, plus also drop across the resistor. So definitely the voltage across the transistor is 2.5 volts, and that would put it in the active region. If you draw less current, these numbers will go up. So our output voltage is going to be dependent about how much current we draw from it. We're going to fix it up by using a Zener diode in an application in the next video. If you were to use a smaller power supply, the numbers will be dropping also. Let's find those specs in the data sheet. So going back to page 124, here are the specs when the output voltage is low and high. So with a 15 volt power supply, depending on how much current that we're sinking, giving the values that we had back in the lecture notes. And when the output goes high, same thing. Here we've got sourcing current, and the output voltage is a couple volts below the power supply. There's also plots of the output voltage drop versus the output current on page 125. Let's take a look at that. It's on the next page. That's a plot over here. So here the output voltage is high, and we have a drop between the power supply and the output. So it's giving us the difference of those two as a function of temperature and a function of the amount of current that we're supplying. And it's given here over a range of power supplies, but it's taking the difference of the two. It's just merely one plot for a given temperature. So if we're sourcing, say, 100 milliamps of current at 25 degrees C, we're looking at a drop difference between 1.6 and 1.8, and maybe 1.65 or so. The numbers in these graphs aren't always the numbers that are in the table, because this is specifically one chip that they're measuring that had picked as something typical. And then in the table, you might get an averaging of data. Go back into the notes. There's also specs for the rise and fall time of our output. And on page 124, typically it's 100 nanoseconds for the rise time or the fall time, but could be as large as 200 nanoseconds. Let's go find it in the data sheet. This is back on page 124 again. You can see here there's a rise time and fall time. Typical values and then maximum values. Our last spec is the supply current. Turns out when the output's low, the timer draws the most current. Page 124 again, we'll see a spec for 15 volts and 5 volts, and typically it's drawing 10 milliamps of current. Now compare that to a 741 op amp, it's drawing about 1 milliamp of current. So it's consuming quite a bit of power. The CMOS version of this chip draws a lot less current, but it also can't drive as much current. So it's a trade-off depending on what you're kind of hooking up your circuit to. You can also find plots of this on page 125. Let's go find the spec on the supply current in the table, and then we'll take a look at the plots. So here's our supply current in the low state for a 5 volt and a 15 volt power supply. Here's our 10 milliamps and our 3 milliamps. This is for a load that's basically an open circuit. Now if you put a load that isn't an open circuit, then you're going to have to add that current. That's where all the current's going to come from, is from the power supply. Let's take a look at then at the plots on the next page of supply current versus supply voltage for different temperatures. There's not a big change here, but you can see for a 15 volt power supply, here's our 10 milliamps or so we were talking about. And this is the 555 timer SPICE model and the data sheet for the 555 timer.